Good afternoon and welcome to the first hearing of the Disruptor Series in the 115th Congress. Today, we're focused on advanced materials and production methods. The panel of witnesses are experts in a number of different fields, from graphene and other nanoparticles to bioink and techniques to 3D print human tissue. We also have experts in new materials and fabrication methods developing plastics, metals, and composite materials. The potential for each of these materials, and even those that may not be represented on the panel today, are subject to the health of the U.S. economy and the willingness of public and private investors to take some of the amount of the risk. However, on the other end of the equation is the potential for the improved safety and long-term cost savings. There should be a full vetting of the costs and benefits as we examine potential use cases for the advanced materials. Moreover, if we are serious about improving safety, bringing consumers more and better options, and ensuring manufacturing jobs with that Made in American label, then we must be leaders in the development and application of these materials.
Today, our Disruptor Series continues with a look at innovative materials and production methods that are the building blocks for some of the emerging technologies that could change how we see in the world. There's also the opportunity to work with traditional materials to create new composites that could solve some of the competing cost and safety questions. For example, new bridges and car bumpers could both benefit from taking into consideration new technologies. So I'm interested in hearing from our panelists in industry and academia about their experience approaching investors and clients about their products and services. So as we look at the relationship between job creation and our nation's infrastructure, it is crucial that we understand the marketplace and what's currently under development.
At this time, we will recognize Dr. Gangaro for 5 minutes. Thanks again for being here.
Thank you very much, Mr. Chairman. My theme today is going to be on the renovation of American infrastructure with advanced composite materials. Herein, I do not want to propose rip and replace our existing conventional materials. We want to reinforce them, make them safe. According to last week's American Society of Civil Engineers report, our infrastructure received a grade of D+. This low grade is attributed to $4.5 trillion over 10-year funding gap between revenue and infrastructure needs. On top of it, motorists are spending $500 a year per vehicle to maintain due to the poor quality of our bridges and highways. Where could we get the funding from? Public-private partnership. We have been doing that to a small extent, and as you have seen, I-267 outside DC. More debt to our $20 trillion debt package. Not sure that the Congress wants this route. Increase in federal and state gas taxes. That, I'm afraid, doesn't have the appetite of the Congress. I have a fourth idea. Do not rip and replace, but renovate with advanced composite materials. Here are some of the composite materials that we at the Constructed Facility Center of West Virginia University have been developing since 1987. Thanks to Congressman McKinley, we built a bridge in his backyard back in 1996. It is standing, functioning extremely well with a reinforcing bar in lieu of the steel bar. This is 4 times lighter, 2 times stronger, non-corrosive, non-conductive. I have several materials to that effect. These developments have taken place in cooperation with government agencies, a wide range of industries, and academia. To illustrate West Virginia University activities with government and industry help, we have built over 100 new bridges, including laminated composite timber, polymer, and glass or carbon composites. And also we did some of the hybrid development, implying the wrapping of concrete and timber with composites. And these approaches do not call for any rip of the existing commodity products, but reinforce these products with glass or carbon as a shell with conventional materials as a substrate or a core. Today, I want to focus on discussions on saving huge sums of money for taxpayers without compromising safety or user inconvenience. Allow me to use 3 great examples to illustrate my savings plan, say, for example, with focus on transportation infrastructure. One is the bridge deck systems. These are the first lines of defense when it comes to structural material deterioration of bridge superstructures. This is a $120 to $150 billion problem. We can remove the spalling concrete and do few other things and put a glass or a carbon fabric carpet on top of the existing concrete deck and fuse it with proper resin. Where is the savings? This can be done with about $50 to $60 a square foot of a deck, while in fact a rip and a replace will cost you about $150 to $180 a square foot. You can imagine the savings. The second example, we discard 20 million railroad ties that are creosote treated, and this has a humongous environmental problem. What we propose is put a Band-Aid known as a glass composite wrap or a carbon composite wrap to enhance the service life to about 50 to 60 years, if not 80 years. Imagine the amount of money one can save we have done the field testing and also the Pueblo, Colorado testing, and we have shown that the life expectancy can be tremendously improved. The third item I'd like to talk about is the shale gas movement. West Virginia is the epicenter of gas deposits. With these new composite materials with nano coatings made of graphene or whatever that are non-corrosive and non-conductive, we can design pipelines with internal pressures of 3,000 to 5,000 psi and be able to push more gas at a most economical price. I have several other examples. I need to skip a few of them for the sake of time factor. Then the question is, one wonders if these are all so good, why the free market is not accepting them. There are several impediments. I will not go into them. In conclusion, those impediments are clearly stated in my write-up. However, in conclusion, this is what I'd like to say. We are most grateful that the U.S. government support has been integral in the initial development and implementation of composites in civil infrastructure. With continued support, manufacturers will continue to expand, create high-paying jobs, and improve U.S. infrastructure so that advanced composite materials will be integral part of our infrastructure landscape. Thank you very much for the opportunity.
And again, thank you very much for your testimony. And Mr. Wyant, we'll give you 5 minutes now for your opening statement. Thanks for being with us.
Good afternoon, Chairman Lada, Congressman Matsui, and the members of the subcommittee. Thank you, and I appreciate for the opportunity to testify before you today. I am testifying on behalf of Creative Protrusions and my fellow members of the American Composite Manufacturers Association. Creative Protrusions is one of over 3,000 manufacturers of composites who are represented by the ACMA. Since World War II, this industry has made products using combinations of glass or carbon fiber reinforcements and tough engineered polymers. The resulting material is stronger than the constituent materials individually. Composites provide characteristics specifically tailored for maximum performance in a host of different applications. Composites are stronger than other materials such as steel, concrete, and wood. They are also lighter, more energy efficient, and easier to transport, assemble, and install. They offer design flexibility and durability, and most importantly, are resistant to corrosion and structural degradation. We have been in business for over 44 years and have seen many changes to the industry. Some applications for composites have been disruptors, but are now common practice, like fiberglass boats and windmill blades. The industry has great potential to upend traditional infrastructure and construction markets and address an immediate national challenge. Nearly every key development in our industry since its inception began in the United States. However, the committee should be aware that other countries have accelerated research and commercialization in an effort to gain market dominance. Policymakers should ensure that disruptive domestic technologies like ours have a framework and environmental to encourage their continued advancement and adoption, including supporting institutions such as the Advanced Manufacturing Institutes. Our energy and communications infrastructure is more critical than ever, yet it is reliant upon 19th century technology, wood poles. Tens of thousands were wiped out by Superstorm Sandy, and hundreds of thousands of wood poles and crossarms are nearing or past their functional service life. We have a choice to continue with this outmoded technology or use 21st century material. My company is one of many manufacturers of composite utility poles and crossarms that are easier to install and more durable against extreme weather, fire, and require less maintenance, and lastly, significantly longer. Composite poles are the best choice in environmentally sensitive areas because they will not leach toxic chemicals and are resistant to rot and pests. The structural capabilities of composites give these materials the ability to disrupt the 150-plus year span for building bridges in this country as well, a disruption welcomed by Canadians and other nations. Composites bring the advantage of extended service life and superior performance through the inherent resistance to rust and degradation. When traditional materials such as steel reinforced concrete rust, crumble, and spall, composites remain unchanged. An additional benefit of composites is the speed of production and installation. Traditionally, bridges can take months to build on site. We have installed bridges with the help of Dr. Gangaro, like the Market Street Bridge in Wheeling, West Virginia, with less than 14 hours of labor to install the bridge deck. The recent events in Flint and Oroville show our water infrastructure is also in need of modernization. Composite technologies have the capacity to revolutionize the water systems around this country. Composites can provide pipe and structures that are easier to install, stronger, and more durable than the other materials, and are inert and don't leach chemicals into drinking water. Composites also have a game-changing potential in marine infrastructure. Our Superlock sheet piling system, for example, rehabilitates deteriorated waterfront structures subject to harsh marine environments. A similar product, our Fender Pile system, was used to rehabilitate the service dock at the Statue of Liberty in wake of Superstorm Sandy, replacing outdated wooden structures. Standards are a crucial issue. The federal government has been instrumental in the development of standards for over other industries. Now is the time for federal agencies to work with us and our academic partners, like my fellow witness, Dr. Gangaro, to develop these standards that would allow us to meet the challenge of our future with innovative solutions. Thank you for the opportunity to testify today on behalf of the domestic composite industry, and I am happy to answer any questions.
And Mr. Wine, if I could ask you, you mentioned something that caught my ear, that you had a bridge deck that went in 14 hours?
Yes.
And how big was that deck, just out of curiosity?
The actual bridge in Wheeling was 200 feet long and approximately 68 feet wide with the sidewalk.
In 14 hours?
That deck was installed in 14 hours. So knowing concrete would be probably a 30 to 40 day just on the deck itself to disrupt, the traffic and delays.
Yes, one more question. I was curious, I live in Sacramento, we have two big rivers, and we're always talking about water infrastructure. So I was curious because some of what you're talking about might be very helpful for us if we're thinking about materials that would be stronger and be able to withstand more pressures and things like that. Are there available, when you build bridges, are you also thinking about dams and levees and things like that also?
Yes. We have great bit of funding from the Army Corps of Engineers, and we have recently, about 3 years ago, rehabilitated a dam underwater without draining it out using the composite materials.
Oh, that sounds pretty good.
Mr. Wyatt, if I may ask, you mentioned a number of industries leveraging fiber reinforced polymer composites in the U.S. from aerospace, automotive, defense, healthcare. How has your company had to adjust to new materials entering those industries over the years?
Well, the big adjustment is trying to develop standardizations that don't exist for advanced composites. A lot of traditional materials, there's handbooks that exist. Dr. Gangaro can pull out a steel handbook. So the big challenge I would challenge and ask for is to help develop those standards. A lot of these companies are very small with restricted budgets, but if the government and universities and industry could develop standards to penetrate, so any engineer out of school could pull out a standard and develop around these products, that would be a great return.
Great, thank you. Dr. Gangaro, how large is the market for composite infrastructure applications? What do you envision?
As I indicated, we are dealing with a $4.5 trillion market in the infrastructure arena for the next 10 years. If I had to make a guess at it, we can easily capture a $1 trillion type market in the next 10 years, provided we do certain things right, as Shane pointed out and a few others, and I also put it in my testimony.
Okay, great, thank you. And also, Dr. Gangaro, in your testimony, you discussed the societal impact of developing advanced composites for infrastructure applications. Can you please explain this in a little more detail, that impact? And is there also a monetary benefit to using advanced composites, and if so, in what ways?
Let me start with the monitoring aspect of it. For example, the longevity of a given system can be enhanced using the composites, not necessarily displacing existing conventional materials, but hybridizing the conventional materials with the composites. I gave you one such example. Take the case of a bridge deck. I believe we can save in the next 10 years several $billion, perhaps up to $50 billion just on one aspect of that. Then let me move on to something like the railroad ties, where the operational costs are tremendously high today. Herein, if I can increase the life expectancy from 10 years, which is what it is today in Southeast United States, to 40 to 50 years, then I can have a huge savings there. For example, New York City today pays $2,100 a tie for replacement, even though the tie cost is only $100 to $150. $2,100. Now, if I can break the cycle of once in 20 years to once in 50 years, imagine the amount of money we're going to.
Right. Well, thank you, and thanks to each of you, and my
Yes,
time's
sir.
expired. I yield back.
5 minutes.
Thank you, Mr. Chairman. Dr. Gangaro, when I read your testimony, if I could be paraphrasing a little bit, you're saying that one of the things, the obstacles we have, barriers that have been put up about our composite construction is being able to evaluate the durability and the cost savings over time. How would you suggest we do that? Which agency should be funded to do that, or how would we go to rectify that problem?
We have been doing some work already in the area of durability, and there is a lot that needs to be done. And some of the agencies that have been funding are the National Science Foundation, the Army Corps of Engineers, the Department of Transportation. So these are some of the agencies.
Are you suggesting that we put some language in to make sure as projects go ahead that they check for that long term?
That is correct.
Okay, thank you. Yeah.
Big picture, and it doesn't just have to relate to infrastructure, but I use that to illustrate the point, to ask the question, are there shortcomings or are there not shortcomings in the analysis on how much it will cost, what the return on investment is, so that as policymakers, we're in a position to say, well, we can do that project for $10, or we can do that project for $15. But if we do it for $15, it's going to be twice as value added to the public benefit because of the materials that we're using and the way that we're designing and building a project. And I don't ask that question just of you. I welcome everyone to answer it. But I think that there's something to that. I just don't know if, in addition to the technology and the advancements all of you are making, whether we as policymakers and the public has an appreciation for that analysis, so that when we make decisions, we're able to justify spending more.
As scientists, we have been struggling to answer that question with a degree of accuracy. One of the best ways to do it is we have been building these infrastructures for the last 25 years, and we need to field monitor them today and see how well they are doing. We have certain mechanisms of establishing the remaining life, thus we should be in a position to establish a decent number in terms of the durability of that product. Once we have that done, then we can translate into a reasonable life expectancy of that product. That's issue number one. And issue number two, when you keep talking about the cost, we need to be talking about how best can we scale up in terms of low volume productions to high volume productions. Once we have these two sorted out, recognizing the fact that certain costs will come down with experience, with certain kinds of insights into what we have been doing. So these are the three different factors that need to be looked at to get you a decent projection of how much it's going to cost.